Right now, wherever you are, you have a device in your pocket that communicates with robots in space. You open a map to find the nearest coffee shop or order a taxi, and a blue dot on the screen instantly shows your exact location. We've gotten so used to this that we don't even stop to think about how incredible this technology is. But what if I told you that your phone doesn't actually know where you are? It doesn't measure distance at all. All it does is track time. And to ensure that tiny blue dot on the screen isn't off by even a single meter, humanity has had to launch dozens of highly complex spacecraft into space and even apply Albert Einstein's theory of relativity. Today, we'll take the GPS system apart, piece by piece. You'll learn how the magic works that keeps airplanes from colliding in the sky, ships from getting lost in the ocean, and your pizza delivery person from always finding the right door. Spoiler, it's much more complicated and interesting than it seems. The acronym GPS stands for Global Positioning System. It's based on a constellation of at least 24 active satellites, though there are usually more, about 31 for reliability. They don't just hang around in one place. These high-tech birds circle the Earth at an altitude of just over 20,000 kilometers, traveling at a speed of about 14,000 kilometers per hour. Every 12 hours, they complete a full orbit around our planet. The orbits of these satellites are calculated with mathematical genius. They're positioned so that at any given moment, anywhere on the globe, from the Sahara Desert to downtown New York City, there are at least 4 satellites above your horizon. This is a critically important number, and you'll soon understand why. Many people think that a phone sends a signal into space. A satellite picks it up and says, "Ah, there you are." But that's a myth. Your phone is exclusively a receiver. It doesn't transmit anything toward the satellites. The satellites themselves continuously broadcast radio signals in all directions, like space beacons. And these signals contain just 2 main pieces of information: who I am, the satellite's ID, and the exact time this signal was sent. And this is where it gets really interesting. GPS is a system that measures time, not distance. Imagine this. A satellite sends a signal that says, "I sent this message at exactly 12 o'clock. Your phone receives this signal and checks its internal clock. Let's say it received it at 12 o'clock plus a tiny fraction of a second. Since radio signals travel at the speed of light, which is nearly 300,000 kilometers per second, the phone can easily calculate how long it took for the signal to reach Earth. Multiply the travel time by the speed of light. Bingo! We get the exact distance from your phone to that specific satellite. But there's one huge problem. For this math to work, the time must be incredibly precise. An error of just 1,000th of a second will cause your phone to miscalculate your location by 300 kilometers. You'll order a taxi in Moscow, but it'll show up somewhere near Ryazan. That's exactly why every GPS satellite is equipped with an atomic clock, the most accurate timekeeping device ever created by humans. They gain or lose at most 1 second over several million years. But your phone doesn't have an atomic clock. It has a regular quartz oscillator which is constantly off. So how does the phone calculate distance with such precision? That's where pure geometry comes into play. The process by which your phone locates you is called 3D trilateration. It sounds scary, but it's actually quite fascinating. Imagine that your phone has received a signal from the first satellite and determined that it is 20,000 kilometers away from it. This means you could be anywhere on the surface of a giant invisible sphere with a radius of 20,000 kilometers, with that satellite at its center. Then the phone picks up a signal from a second satellite. Now we have a second sphere. The intersection of the 2 spheres is a perfect circle. You're somewhere along the circumference of that circle. We pick up a signal from a third satellite. The third sphere intersects our circle at only 2 points. One of these points is usually somewhere in deep space or deep underground, so the phone discards it. The remaining point is you, your latitude, longitude, and elevation above sea level. It would seem that 3 satellites are enough, right? Yes, if your phone had an atomic clock, but since it doesn't, your phone's clock isn't synchronized with space. And that's why we need a 4th satellite. The 4th signal allows you to solve an equation with 4 unknowns: latitude, longitude, altitude, and time. It instantly corrects your smartphone's internal clock. Essentially, the moment you connect to GPS, your phone becomes equipped with an atomic clock for a fraction of a second. If you think the challenges end there, hold on tight. Because the engineers had to contend with the universe itself. They had to turn to Albert Einstein. According to the special theory of relativity, time flows more slowly for objects moving at high speeds. Satellites travel very fast, 14,000 kilometers per hour, which causes their clocks to lag behind those on Earth by 7 microseconds per day. But there's also the general theory of relativity, which states that gravity also warps time. The farther you are from a massive object like Earth, the weaker the gravity, and the faster time passes. At an altitude of 20,000 kilometers, Earth's gravity is significantly weaker than at the surface, so a satellite's clock runs 45 microseconds fast per day. All told, time on the satellites runs 38 microseconds faster every day than it does here on Earth. It might seem like a mere trifle, right? But because of the speed of light, if engineers hadn't factored corrections for Einstein's theory of relativity into the equations, the GPS error would increase by 10 kilometers every day. The system would become completely useless in just a couple of days. That's why physics, which seems like an abstract theory from textbooks, literally comes into play every time you open your navigation app. GPS has long since been about more than just finding your way to a destination without getting stuck in traffic. This system has become the literal invisible nervous system of modern civilization, and its influence extends far beyond navigation. Have you ever wondered how your mobile internet and cell service work? When you're driving and talking on the phone, your signal is constantly being relayed from one cell tower to another. To ensure this transition is seamless and the call doesn't drop, the towers must be perfectly synchronized with one another, down to the microsecond. And this synchronization is provided by the precise time signals from GPS satellites. If you turn off this cosmic metronome, cellular networks will begin to malfunction and over time simply break down into unconnected segments. Now imagine the global financial system. On stock exchanges, algorithms execute millions of high-frequency trades every second. In a world where fortunes are made or lost in milliseconds, it is critically important to know exactly who bought a stock, when, and at what price. Every financial transaction, every bank card transfer or cash withdrawal at an ATM receives an electronic timestamp synchronized to GPS atomic clocks. If the system fails, the global economy will plunge into utter chaos because bank servers will be unable to determine the correct sequence of payments. Let's move on to the electric power sector. The power grids of entire countries operate as a single, living organism. Alternating current flows through high-voltage wires, changing direction dozens of times per second. To combine energy flows from nuclear power plants, wind turbines, and solar panels into a single grid without short circuits or blackouts, the phases of the current must be perfectly synchronized over thousands of kilometers. To achieve this, smart sensors are installed at substations, which synchronize the pulse of the entire power system hundreds of times per second. And yes, they derive this ultra-precise rhythm from GPS satellites. In aviation, modern aircraft use the ADS-B system to transmit their coordinates to air traffic controllers and other aircraft every second, preventing collisions even in zero visibility conditions. In agriculture, giant combine harvesters travel across fields on full autopilot with an accuracy of a couple of centimeters, saving millions of metric tons of water and fertilizer. We have created a colossal, highly complex infrastructure on Earth that is entirely dependent on a fragile radio signal traveling from the void of space. To give you an idea of the scale, the signal's strength from a satellite upon reaching our planet's surface is comparable to the light from a 20-watt light bulb that you're looking at from a distance of 16,000 kilometers. And yet, this faint, invisible thread keeps our material world from descending into chaos. It is both our greatest technological achievement and our biggest hidden vulnerability. If you were curious to take a peek behind the scenes of the technologies we've grown so accustomed to, give this video a like and be sure to subscribe to the channel. Let us know in the comments, did you know that Einstein helps you order taxis and pizza? There are still many mysteries of our world ahead that are worth unraveling. See you in the next video.